Hello to everybody, and welcome to this second webinar. This webinar series that we are doing, focused on different aspects on the electrical mobility. Today, we will talk about the design and the management of the different thermal management systems focused on the electrical mobility on different electrical vehicles, since these designs are a little bit tricky when we are working in these applications, and especially when we are working with the new wide bandgap semiconductors. So today we have two brief presentations, about 20 minutes each presentation. And at the end of this presentation, we will have a brief Q&A session. So our first speaker is Arman from the Irish University. Hello, Arman.
Hi, David. Thank you for your invitation, and just let me know when I should when should I start.
You can start now.
Okay. So first, I would like to say thank you for your invitation and say hello to all. Thank you for coming. And so I'm Arman, a postdoctoral researcher in the Electrical Energy Technology Group at Aarhus University, and today I want to talk about the thermal management system for high-speed power converter in a heavy electric vehicle. And all the activity, all the different slides that I will present in this session is in the framework of the RHODaS project. In the project that we are working in the high-performance power converter for the heavy-duty electric vehicle. So I will start with the high power converters. When we talk about the high-speed power converters, we should talk about the wide bandgap material and semiconductor. And the most important one is the silicon carbide or gallium nitride in the power converters. We know that they have a lot of capability over the years. We could see the progress in the right-hand side, the timeline for the major packing and cooling innovation. You can see in the right-hand side, the first mass production of the SiC MOSFET was in 2010, for example, and the first commercial enhanced mode GaN power transistor was in 2009. We know that the GaN transistor is a little bit behind of the SiC transistors and semiconductors. So we have better current and and better high power performance in the SiC power module. I will talk about it and what was the result of this different in the RHODaS project. But in the left-hand side, you can see the comparison between the traditional silicon-based semiconductor with the GaN and SiC power module in different aspects like electric field, thermal conductivity, melting point, electron velocity, energy gap, and different part. And we can see that the wide bandgap have been shown the high voltage operation, high frequency switching, and high temperature application. Briefly, we can say that they have higher efficiency, superior switching performance, better reserve conduction behavior, and high voltage capability. But we know that we have a lot of capability, but there is one restriction. And the restriction is the power losses and the temperature. When you like to go to the high frequency, high switching frequency specifically, because usually with the silicon and with the IGBTs you could go up to 100 kilohertz, but you can go easily from 100 kilohertz to 100 megahertz with the wide bandgap, and with the ultra wide bandgap material you can go more than 100 mega. You have this capacity, but there is a big restriction in front of you, and the restriction is the thermal management system, because you should be able to manage this switching, this fast switching. When you have fast switching, you have more power losses, and when you have more power losses, you have more heat generated in your system, and you should be able to manage it. Just I have in the right-hand side of this slide, I bring a statistic of the causes of electronic equipment failure that shows that more than 50, or is better to say that 53% of the whole failures in the power semiconductor-based material coming from the temperature and temporal stress. It's significant, and the key indicator of this thermal management system, or thermal cooling, or cooling system, or thermal controlling of different the semiconductor or power electronic devices is junction temperature. Junction temperature is the indicator that you should be sure that you maintain that parameter below the restriction. Just to give you some understanding about the restriction that we are faced, for example, in RHODaS project, we work with different power converters. The first one was a low power converter, and second one was a high power converter. I will tell you about it in the next slide, but based on this different power converter, you have different thermal management technique. So I can say that the bad news is we cannot tell you what is the best thermal management technique for all the applications. Based on different application, based on different power level, based on different capacity, and different requirement, you might use different type of cooling system. And we had this opportunity in the RHODaS project to use two different technique and two different thermal management system for a different level of the power converter that I will tell you in the next slide. But briefly, we can divide the cooling system into the air-cooled system, liquid-cooled system, another cooling system that is combination of air-cooled power cooling system, liquid-cooled, and maybe gas-cooled power system, that you should be able to calculate it based on the requirement of the project, and to select this different approach based on the needs in your application. The first step to go through a process and a systematic process for designing a thermal management system is to do some calculations, some basic calculation. Mathematical calculation and analytical modeling are the most important part. We know that when we talk about the mathematical calculation, we talk about the simplified model, we talk about some rough calculation, we talk about some references, but they are necessary because you should have some understanding about different part of your system. How much cooling capacity do you need, and which type of cooling system is the best for your system? What is the space you have? What is the how compact you need this? Do you have any place for different material and different part and components that you need in the liquid cooling system, or are they necessary or not? So in the RHODaS project, we start with some calculation. Our experience said that these calculations are simplified, but they could show good presentation of the system. We didn't have only one cooling system for the power converter, or it's better to say inverter. We had a cooling system for the electric machine. So we work on it, and after that, during the process, we got to know that these calculations were promising. Because of that, we built a user-friendly toolboxes for each calculations, each sets of calculations. So they are very easy to use, and you have some place to add some initial parameter for your system, and after that, they will come up with some suggestion and some requirements for your system in the inverter or in the machine design. And the good news is, after the RHODaS project, we will publish them, or before the ending of the RHODaS project, we will publish them as open access tools, and researcher and other people can use it and can use it in design and process. So this was the first step. We had two different power converter, as I said, in the RHODaS project. The first one was for the proof of concept. That was the RHODaS low power converter. You can see here in the picture. Both converters are built based on the topology of T-type power converter, because we are using GaN and SiC power module, both in one topology. And T-type power converter is a interesting power converter. I'm pretty sure that David, in the first round of presentation and webinars, talk about it in detail. But for those who don't know and who couldn't participate in the first one, the T-type power converter has one middle point and middle leg that you can use it for the power converter with low current, and you can use the other two leg for the high current power converter and power modules. So we use SCAPE modules in the two legs, and we use GAN module for the low current leg. And you can see here, because of the capacity and the size of the power converter, we could remove all the complexity of the air-cooled, liquid-cooled power thermal management system, and we decide to go for the air-cooled thermal management system. But for the high current and the high power converter, we couldn't go for the air-cooled, and we decided to go for the liquid-cooled thermal management system. In the liquid-cooled thermal management system, you have your power converter, and after that, a heatsink or cold plate coming through a pump, a radiator, fan, and a circulating liquid that is usually, 50% glycol and 50% water. You would control and the junction temperature of the different semiconductors and different modules. You have the control unit as well, that in the case you want to control the flow rate and you want to control the pump speed of the system, it gives you more more opportunity. So you can see the heatsink that we built in the RHODaS project for the low power heatsink, and the thermal management system that we built. This is the medium scale thermal management system that we built it for the proof of concept, and after that we will use it in the RHODaS infrastructure. One of the most important part in the thermal management system is heatsink, and heatsink is critical because the heatsink is the part that is in contact with your power module. So the topology of the heatsink is very important. As I said, we had air-cooled power converter, the thermal management system, and liquid-cooled thermal management system, and for each of them, we start with designing different topology. This topology wasn't just the body of the heatsink. You can see, for example, in the liquid-cooled, we had different topologies, different geometries for the body, different fin and pin arrangement, and different size. And one of the key important things in the liquid-cooled heatsink was that hole that we built into the heatsink. It was very difficult to handle this hole because, in the printing, in the building and manufacturing with these heatsink, it caused a lot of problem. But after that, the result is you will have a good mounting pressure. That is very important. Heatsink is important, but mounting pressure and thermal interface material as well are very important. Just as an example, I can say that with changing the thermal interface material and mounting pressure, you can change the heat dissipation up to 40%. It's a lot. So let's discuss about this heatsink in the low power application that was air cooled. We had we had a S-step and the two different height in the PCB for the SiC and GaN part of the low power converter. So because of that, we wanted to minimize the the height of the thermal interface material. So we built a S-step on top of this heatsink, and after that we had a different round of optimization for the type of fin and the geometry of this air cooled. We use console and multi-physics simulation to optimize this heatsink, and maybe you ask me that why you select this time-consuming the application for modeling your heatsink. They are time-consuming, but on the other hand, they are very accurate. So we are always dealing with this trade-off of computational time as well as the accuracy. But we had our own procedure, our own technique for using the console. If you want to optimize something in console, it will be very time-consuming because each iteration, not in the air-cooled power converter. I think for the air-cooled thermal management system, it takes something like 1 hour, 2 hours each iteration and each simulation. But sometimes in the liquid cool, it takes 8 hours, 9 hours. So if you want to use the normal iteration-based optimization algorithm, it's more or less impossible, because you need to run different simulation up to 1,000 iteration, 500 iteration, and with the capacity we have and with the time that we are in the applied project and ITRL project, it's impossible. So we combine multi-physics simulation with the engineering understanding, and after each iteration we discuss the result, and after that, based on that result, we say change something and we get the next result. And in this the procedure, we reduce a lot from the iterations based on this engineering understanding and discussions. You can see here some of this result in the console, different active area temperature, and as I said, for the GAN module we had something like 150 as a maximum temperature in the GAN module, and in the SCAPE module we had something like 175, a little bit more. After designing the topology of the converter, the topology, I'm sorry, I sometimes have some mistake in the converter and thermal management system, because we are usually working with converter as well. So when you have this heatsink and when you finish with the geometry of this heatsink, now it's the time to optimize the other variable in your heatsink. Heat transfer coefficient is very important, and it's related to the fan and the speed of the fan. And here you can see, in a sensitivity analysis that we have run, you can change the maximum temperature in the SIG part from 84 degrees centigrade to 60 degrees centigrade, 20 degrees centigrade, by just optimizing the heat transfer coefficients in the fan and by tuning the fan. The next part of our project was related to the high power converter, and we wanted to integrate this high power converter in the whole motor, gearbox, and inverter infrastructure. So for that one, we need to use this liquid cooled heatsinks. So we start again with a normal heatsink with some hole to be sure that the mounting pressure is good, and we work a lot on the thermal interface material as well. To make sure that they are optimized, we had two different heat source, and we optimized everything based on and we tune every parameter based on the data sheet in the GAN and SIG and the configuration of the power module. So you can see here, different round of optimization. For example, this was about the height of the power converter, the height of the heatsink. So the height of the heatsink was very interesting for us. I don't want to go through because we don't have time. And so not always more height is better for the heatsink. We had different the optimization on the body and on the location of inlet and outlet, as well as we designed one heatsink for the project, because we decided to combine the heatsink for the GAN and SIG part of the power module. So we integrate both of them, and we put 4 holes for the GAN power module and 4 holes for the screwing the SIG power module with different hot spots, and we did different detail simulation for this heatsink. When we finished with the design, again, like the air-cooled heatsink, we went through the optimizing different variable. For example, one of them was the inlet velocity. So what should be the best inlet velocity? And you can see here, by changing inlet velocity from 0.3 meter per second to the 1.8, for example, you can go from 80 to 40 degrees centigrade. And based on these iterations, we simulate different parts of the heatsink, and we optimize different parameters for the heatsink. I don't want to go to the detail of these different figures. After that, we can discuss about it if you are interested in the QA session. We built and we manufacture these two the heatsink first in the copper, because copper has better characteristic for the thermal and heat dissipation. But unfortunately, because of the hole, we couldn't come up with a good 3D printing procedure without any leaking, because leaking was a big problem and could be a very big problem when you have DC link voltage of 1000 volt. So in this case, we change it to the aluminum, but this change we simulated, and you can see here the T maximum for the aluminum is something like 29, but for the copper is 26. Yes, definitely copper is better. But based on this restriction, we changed it to the aluminum, but on the other side, we had a lot of weight reduction, something like more than 60% weight reduction. That could be an advantage, and in this case could be an advantage for the whole system. Weight. The last part is the thermal management system testing, and we have tested with the help of our colleagues in Bosmo. And the result of this system in both air-cooled and liquid-cooled heatsink was acceptable, and we could integrate it. And I think, in the RHODaS project and in the framework of the RHODaS, we will use it, and we will come up with the final result. Before finishing my presentation, I would like to say that I wasn't alone in this activities, and I want to say thank you to our team members, Cornelio, Uwe, Jorgen, that they help us, and they was in the process of design and optimizing different things. And at the end, I want to say thank you to the whole colleagues in the Electrical Energy Technology Group and RHODaS team. Thanks a lot.
Thank you very much, Arman, for your presentation.
You're welcome.
So the next and the last presentation before the Q&A session, our next speaker is Xavier Jorda. Welcome, Xavier.
Hello, thank you very much, David, and thank you also for the opportunity to share our experiences in the framework of the SCAPE project. Thank you very much.
You're welcome.
I go ahead with the
Yes.
presentation. Okay, then let me share the screen. Now. Okay. Okay. Sorry. Yeah. Please, can you confirm that it's okay? Yeah, I think it's okay. Perfect.
It's okay.
Okay, let me activate the pointer. Okay, then thank you again. My name is Xavier Jordan. I am a researcher at the Institute of Microelectronics in Barcelona in the Power Devices and Systems group. And I will try to summarize our experience in developing elementary building blocks for developing power converters using the chip embedding technology, with a special focus on the first results we obtained with this technology concerning the thermal behavior of these power converter solutions. The outline of the presentation is this one. I will start with a brief presentation of the SCAPE project in order to give an overview of the motivations for this work. I will make also a brief introduction to the chip embedding technology. Then I will explain how in SCAPE project we take advantage of this technology. And then I will go with two aspects of the thermal behavior of the converters or the modules, let's say the modules we have developed using this technology. Let's start by the motivation of this work. SCAPE project objective is the development of modular and scalable electric vehicle power electronic design and implementation methodologies to cover a wide range of vehicles, going from the two wheels to trucks. I suggest to review the first session of these webinars which was presented by Professor Sergi Busquets, who has gone more in detail on the power electronics topologies, architectures, and controls, etc., regarding this project and this let's say motivation. In any case, you can see here very clearly the idea. The idea is to have elementary building blocks that can be replicated in order to increase the power by either increasing voltage or increasing current of the converters that will be used in different kinds of electric vehicles. As I mentioned, this problem has been assessed by different approaches. One is the power electronics, let's say, approach, or by developing different architectures, different topologies, mainly of them based on multi-level converters. Another approach is also on taking advantage of integration technologies, different from the conventional ones. In SCAPE, we have focused on developing these smart switching cells as the building block for developing the different converters that will be used in the electric vehicles. As an example here, for example, the traction inverter of a vehicle. The traction inverter, if we go from right to left, it's based on several converter legs of a multi-level topology converter leg, which is integrated by the replication of a number of individual switching cells, which show the behavior of a smart, that means intelligent, bidirectional current switch and unidirectional voltage switch. This building block is based, in our case, on 750 volts breakdown voltage silicon carbide MOSFETs. And the idea is that this building block, this switching cell, is smart in the sense that it integrates the gate drivers, protection circuits, sensors, communications, and even self-powering circuits, as I will explain later on. Conventional solutions for the implementation of the converters, you know better than me, are based on conventional power devices packaging solutions, multi-chip power modules, discrete devices. More advanced solutions like double-side cooling modules are also possible. But in any case, we have a combination of several elements. The control, even the first level control, which activates the power devices switches, the gate drivers, etc. Secondary controls, etc. We need to connect these different power devices that integrate the complete converter. Then we need some kind of bus bar of interconnection solutions, and we need a thermal management system. In SCAPE, what we have tried is to analyze and to study a different alternative to these conventional implementation technologies, which is chip embedding. And now I will make a brief introduction to chip embedding. This concept refers to the packaging technologies or the assembly technologies where semiconductor devices or even integrated circuits in bare die format, that means with any kind of packaging, are included in a stack structure, which is usually a laminated PCB multi-layer substrate. You can see here, for example, this cross-section coming from the company Schweizer, where you can see on top standard PCB substrate. And in the cross-section, you can see that among the different copper layers, you can see this blue line. This blue line is, in fact, a silicon carbide MOSFET. Then the power devices are not packaged apart and integrated to the substrate, which contains interconnection layers, SMD components, etc. But the power devices are included, are part of the PCB substrate itself. Here you have this schematic cross-section. It's a drawing to show more clearly the different elements. You can see in this case we have 6 layers of copper, SMD components on top. You can see in blue the power device, which is included embedded in the substrate. You can see that there are other auxiliary elements like copper lead frames, which help on dissipating the heat, etc. We will see later on. And there are also some critical technological elements like copper layers deposited on top of the power devices, and also die-attached layers, which need to be very performant layers in order to achieve good results with this chip embedding technology. As I mentioned, in SCAPE, we were interested on analyzing this solution because we think that it's a very suitable and even an optimum technology for integrating the kind of modular and scalable power modules that that are used in the multi-level converters in the project, allowing the integration of the smart switching cells function. Chip embedding has many benefits. Let me mention only perhaps some of them. The first is the higher levels of integration that can be achieved because, of course, the devices in bare die format, the package of the devices, the power devices in bare die format is the same PCB substrate that is used for developing the whole converter. In addition, in this PCB substrate, we can very easily and in a very optimum way combine the power and the control stage of the converter. In chip embedding, we manage less integration technologies. Basically, we developed a PCB board, and the integration technologies associated to the package of the power devices are avoided. No needs for ceramic substrates, no need for base plates in power modules of encapsulant materials, etc. Then it's a way of easy way of developing customized and easy to manufacture application-specific power modules. Well, in a more practical point of view, chip embedding allows also the reduction of stereoinductance, which is a well-known problem in the integration of wide bandgap semiconductors, basically because of the multi-layer structure of this solution. And other benefits are the possibility to include internal shielding, protection against plagiarism, etc. In chip embedding, in the typical manufacturing process of PCB, we include some particular steps which allow the inclusion of the, in this case, silicon carbide MOSFETs, the inclusion of these silicon carbide MOSFETs inside the PCB structure themselves. As I mentioned before, critical aspects are the die attach. It means the way we interconnect the backside of the power device of the chip to the PCB stack, and also the topside interconnection. The topside interconnection of the chip with the PCB stack is made by the same vias that are used in the manufacturing of the PCB itself. Once the device, the die, has been included inside the PCB stack, at a given moment of the development, the vias are metallized with copper, and these vias, a part of interconnecting different copper tracks as it's their standard use, these vias also connect the top side, the gate and source, for example, in this case, of the power devices. To do that, it is mandatory to have copper metallizations on top of the power devices, of the power chips, which is not always an easy task. If you want more details on this technology, I suggest to you to have a look at the talk that Thomas Godwald, CTO from Schweizer, provided at IMBCNM, and which is available in this link, which was an invited talk in the framework of SCAPE Project General Assembly. Okay, then you have seen what is roughly chip embedding, and you will see now how we have taken advantage of this technology in SCAPE. As I mentioned before, our target is the development of an elementary building block, which is the switching cell that will be repeated n times for the different converters to be developed. And the technology we selected, there are several companies providing this technology, but we selected the high voltage version of the P2PAC technology from Schweizer. It's a 6-layer PCB technology, where, as you can see, and I introduced before, the silicon carbide dies, in our case, are attached to a copper lead frame. These silicon carbide dies are then internally interconnected on the top side with the vias in the PCB stack, and I also stress the fact that on top we have a standard PCB. Then it means that on top we can include SMD devices, for example, the gate driver circuits, which are very close to the device to be controlled, but also other devices, other auxiliary devices, other power devices, for example, the terminals, etc. In our in the solution we propose in SCAPE, this switching cell will dissipate to the backside. I mean, the main heat extraction path that we selected is conduction to the backside, and in the backside we fix a thermal management system that will be based on a liquid cooling solution. This means that in the design of the switching cell, one of the main targets was the dissipation of the heat from the different heat sources to the backside. The design, in fact, of the switching cell is very similar to the design of a standard PCB, except for the fact that we have active devices inside the PCB stack. then this means that particular care can be done to this design and to this implementation. And let me also mention that the design of the switching cells in SCAPE has been the research work of Mariana Raya here at IMB CNM. And I acknowledge her for providing many of the results you will see in this presentation. Well, you can see here the block diagram of the switching cell that we have integrated. You can see that it's based on 2 silicon carbide MOSFETs, as I mentioned before. One plays the role of the main switch. It's really the switch, the MOSFET that is switching at high frequency. A second one, as it was introduced by Professor Busquets in last week, is a second power device which is used for protection functions. This iFuse is called iFuse. Is used to ensure that in case of a given failure, the whole switching cell, the power stage of the switching cell remains in open circuit. And in addition, in the stack, in the PCB stack, we will embed not only the 2 power MOSFETs, but also the shunt resistor, which is used for monitoring the main current of the switching cell. All the control circuitry, the protection, etc., is on the top side. And you can see here a little bit the distribution of the main, the power stage in this side, and the different control protections and etc. of the board. And you can see here the final result of this design and manufacturing process. This is the switching cell we have developed below this PCB area. As I introduced before, one of the main benefits of this technology, the total parasitic inductance is lower than 2 nanohenries. This is achieved by the fact that we can cancel the magnetic fields in the forward and returning currents at the different tracks of the PCB stack. Well, then this is the switching cell that we have developed. You can see here a cross-sectional view of this development. You can see here the shunt, the iFuse, the main switch. Okay, you can see here in gray, this is the silicon carbide power MOSFET. And as I also mentioned before, for achieving these results, it's very critical to have relatively thick, this means between 5 and 20 microns copper metallization on the top side pads of the power devices, on the silicon carbide MOSFETs. And we need also a very good die attach layer. This means the layer which fix the die, the chip of the MOSFET to this copper lead frame. And in our case, we have used micron nanoparticles, silver micron nanoparticles, which have been sintered. This layer, this is the final layer that is achieved using this approach, shows very good thermal and electrical conductivities. In particular, at thermal level, the thermal conductivity of this die attach material achieves up to 200 watt per meter Kelvin, while, for example, typical soldering materials achieve values between, let's say, 20 and 50 watt per meter Kelvin. Then it has been very, very interesting using this material. And let me also mention that the development of these technological solutions has been developed in the framework of Emma Solar PhD research here at IMB CNM again. Here you can see a detail, a cross-sectional view and a microphotography of one of the copper vias in the PCB that contacts the copper layer, which is placed on top of the silicon carbide MOSFET. Okay. From the electrical and functional point of view, these switching cells have worked very well. You can see here the static characteristics, bidirectional current switch and unidirectional voltage switch. Total on-state resistance around 30 milliohms, which is the expected value. High frequency commutation capability at 400 volts and 30 amps. Here we are switching at a frequency of 250 kilohertz. The protections, you can see here the short circuit protection. We introduced a short circuit in the switching cell with a maximum current up to 1000 amps. And this short circuit is correctly shut off by the saturation protection of the gate driver in less than 4 microseconds. And also additional protections, as I mentioned before, as for example, the activation of the I-fuse. The I-fuse operates at 200.5 microseconds when it detects any kind of failure. Here you can see a short circuit failure, an external short circuit failure, which is rapidly shut off by the I-fuse activation, and the complete switching cell remains in open circuit. Okay, then going more in detail to the thermal aspects, the proposed thermal management solution for this switching cell is shown here. Basically, we proposed an enclosure, a plastic enclosure, which redirects the coolant liquid, and the cover of this enclosure is the switching cell itself. In between, we have a thermal interface material and a specific aluminum heatsink placed just below the main heat sources on the switching cell. That means the silicon carbide MOSFETs and some power SMD transistors. The thermal behavior of these systems can be divided into 2 aspects. First one is the thermal behavior, the thermal response of the switching cell itself, of the PCB, chip-embedded PCB, and then the heat transfer between the backside of the PCB and the coolant. If we look at the first aspect, the PCB itself, the elements we have for improving the heat dissipation are the location, the distribution, optimum distribution of the different heat sources on the PCB, and also the distribution of different thermal bias, the design of the copper lead frame, where you have seen that the power MOSFETs are placed, and also the inclusion of different copper areas inside the PCB. All this thermal design work has been supported by COMSOL Multiphysics. And as you can see in this example of a simulation, the most critical elements are the embedded SiC MOSFETs. And we obtain as characteristic figure describing the thermal performance of the switching cell, we simulated the thermal resistance or the complete thermal impedance in dynamic mode or thermal resistance in static mode between the junction temperature of the embedded silicon carbide MOSFET and the backside temperature. During the design phase, you can see that we achieve values around the 0.5 Kelvin per watt, which is an acceptable figure. As you can understand, it's not easy to have reliable simulations if reliable parameters, simulation parameters, are not available. Then, in the framework of our project, one of the main activities we developed is the determination and the identification of optimum parameters for simulation. For example, you can see here in this schematic cross-section, there is a last FR4, or let's say a dielectric layer in the stack, which is very important. This last layer of the PCB stack is very important from the thermal behavior point of view. Then the thermal conductivity of this last dielectric layer in the PCB has a very big relevance on the final thermal resistance that we can achieve. Other critical components can be power devices placed on top, the shunt resistor. In any case, we have identified and we have been able to design the switching cell with relatively low thermal resistance values. These values, these simulated values, have been validated by experimental characterization of the switching cells. We used a standard thermal impedance measurement setup where the PCB is placed on a hot-cold plate, and we estimate the junction temperature of the power MOSFETs by using a thermosensitive electrical parameter. In our case, this parameter was the diode, the embedded diode, MOSFET diode forward voltage drop. Through this thermosensitive electrical parameter, we are able to identify, to measure the junction temperature during the cooling phase, of the switching cell after a steady state dissipation phase. From this cooling curve of the junction and also the backside temperature of the embedded MOSFETs, we can obtain the final thermal impedance curve with which matches very well with the expected theoretical values obtained by simulation in 0.46 Kelvin per watt. Okay. Let me also mention that we have used auxiliary thermocouples inside the chip embedding stack in order to have additional information for tuning these simulation parameters I mentioned before. Well, and concerning the thermal response from the backside to the coolant, we developed this kind, as I mentioned before, of enclosure, which forces the coolant flow, and which also contains the aluminum heatsink that spreads the heat generated in the switching cell and improves the heat exchange with the coolant. The design of this solution has mainly performed by Philippe Lasserre from Deep Concept Company, and also by Mariana Raya, as I mentioned before. And we have characterized this the behavior of this of the switching cell in this liquid cooling experimental setup, and you can see here the values we obtain for different flow rates and the different temperatures achieved in red at the junction temperature. The coolant temperature is 20 degrees C. It's not in incremental, it's absolute temperature. Then you can see that we have this response increasing the flow rate of the coolant with this pressure drop. And you can derive from this that all this information translates in a thermal resistance between junction and coolant of around 1 Kelvin per watt at 7.6 liter per minute. This is a good figure for taking into account the nominal power at which is designed this switching cell. And again, one of our main targets was obtaining a very good modeling and simulation of the experimental prototypes that we developed. And as you can see here, we obtained a very good agreement between simulated and measured temperatures and versus flow rates at the different measuring points of the switching cell. Well, as a conclusion, because I think I'm running out of time, chip embedding, we think we demonstrated is it's a very interesting approach and very well suited for the scalable and modular power electronics approaches that we are proposing in SCAPE, where elementary and validated building blocks can be combined either at hardware level, like we have shown here, but also as at the PCB CAD tools level. Then, I mean, we can build a bigger converter from validated switching cells designed in our PCB CAD tool. We designed, developed, and characterized chip embedding smart switching cells based on silicon carbide MOSFETs, showing very good electrical and functional characteristics, and also showing very good thermal response, mainly when we compare this thermal response of the developed switching cells with discrete devices implementation. The efficient liquid cooling solution has also been demonstrated, and all the thermal effects have been successfully modeled and simulated, providing a very solid base for future developments based on chip embedding. Thank you very much. I'm sorry, I think I have been running a little bit more time than expected.
Thank you, Xavier, for your presentation. So I don't know if you can stay a little longer, Arman and Xavier. If not, we can just make a few quick questions and then you can leave. So let's start with the Q&A session. So please, the people who are watching this webinar, please write in the chat your question, and to whom is for who is the question. So let's start. We have a question for Arman. Yes. It's the following question. How did you model the thermal management system for real-time control, given that full multi-physics simulations are too computationally intensive to solve online?
Okay, so this is a good question, because we know that we cannot use this console simulation in the real time. So as we discussed in this slide, we had two mathematical calculation as well as a multiphysics simulation. But in between these two, we demonstrate that equivalent secret model could be a very good case to be implemented in the real time. And we had some task in the digital twin and real-time control and integrating this different signal to the IoT platform that I think, in the next webinar, our colleagues from Envision will talk about it. But in summary, the equivalent secret model could be a very good case. But you can use and you can optimize and tune the parameters of equivalent secret model with your console simulation, very detailed console simulation. So my response is the optimized equivalent secret model is the best case for the real-time control.
Thank you very much, Arman. We have more questions, in this case for Xavier. We have the following question. Which is the best way to reduce the thermal resistance between the junction and the backside in this kind of chip embedding modules?
Yeah, well, nice question. As I mentioned before, we have several elements we can play with for the design of the heat dissipation path inside the switching cell and the chip embedding board. One of them is the design of this copper lead frame, where the chip, the die, is attached. There is a trade-off, of course. We cannot put a huge lead frame inside the board, but it provides a very nice way of spreading the heat just at the point where it is generated at the power device level. And then also of course the distribution of the different vias, microvias, and thermal vias of the structure. There is a nice degree of freedom for distributing these copper vias and microvias, which provide a very nice way of also spreading the heat and directing the heat flow to the backside and to the areas which are designed for dissipating the heat to the coolant or to the external cooling system.
Okay, thank you very much, Javier. We have another question also for you. Is that the following questions. In order to develop multi-level converter topologies, is it better to integrate this kind of chip embedding switching cells in the same board or connect individual switching cell boards in a common bus bar?
Yeah, this is also a good question, and is one of the topics that have been addressed and probably will be addressed more in detail until the end of the project. At present, we in the framework of our project, we took the decision of keeping this solution of combining different hardware individual switching cells in a common, let's say, bus bar or main board, because chip embedding is increasing it's a technology that it's increasing on popularity, and it's a technology that it's more and more used. But the complexity of some of these multi-level converters requires the use of complex PCBs, and increasing the complexity of the PCB also is risky in terms of yield of production. Then In SCAPE project, as it was the first project where many of us, of the partners, were involved with this kind of technology, we decided to combine the switching cells in hardware mode, and in order to allow an easy replacement of failed switching cells, etc., and to perhaps to keep for future projects the combination of several individual switching cells in the same PCB, complex PCB. And we think that now it's quite risky, and we prefer, in the framework of our project, to be more conservative. But from the performances point of view, I think that we have to go to this complete integration. Yes, of course, but perhaps in the next few years.
Okay, thank you very much, Xavier. I think that this last question was really related with the first explications that we did on the first webinar. So I really recommend to all of viewers to check this webinar if they can. And I think that we don't have more questions. Let me check it. No. So I think that we can call it a day, and that's all. So thank you very much, Armand. Thank you very much, Xavier, for your explanations, for being here. So thank you very much. See you all the viewers on the next webinar, which will be on next Wednesday at the same hour at 3 o'clock. That's all.
Sounds great. Thanks a lot. Thanks a lot, and see you again. Bye.
Thank you very much.
Bye. Thank you.
Bye-bye.
Thanks a lot.